Okay, guys. So finally, we got some quiet here. We might get some more construction noise in the background, so I apologize in advance. And I'll try to make this as fast as possible. Oh, we got some quiet time here. Anyway, so let's see. I think where we finished the common emitter amplifier, the basic one, talking about its details. And just as a quick review, the common emitter amplifier is when the emitter node is the so-called common signal between input and output. What does that mean? Well, when you're applying a voltage, remember that it's always applied between two nodes. So basically the input is applied between this base and ground, and the emitter is at ground. So it's really between a base and emitter is where the input's defined. And when you're reading a voltage, so when you're reading what the V out value is, it's also always defined between two nodes. And in this case, it's really defined if you were gonna put an oscilloscope or a multimeter here, you would put that device between the output and ground. Again, the emitter is at ground, so therefore common emitter is the name of this amplifier topology. So, one of the things that's important to do, as you proceed, move forward in your classes or your job doing microelectronics, is you don't need to derive the gain formula for this all the time. You basically look at this and you figure out, you first thing to do is you recognize it's a common emitter amplifier. You look at the bipolar transistor with emitter grounded, a load resistor to supply, input coming to the base, output coming out of the collector. You go, aha, common emitter. And then so immediately you figure out once you figure out bias point, so VBE, VCE, and I sub C. So VBE gives you I sub C, and the collector emitter voltage tells you if you're in the forward active mode or not. So once you've done that, the gain of this device is minus GM R sub C, where GM is I sub C over V sub T. Your input resistance is the R sub pi of the transistor, and we know that's defined as beta over GM, and our output resistance is just R sub C, assuming RO is 0, which is the same as assuming that V sub A is infinite, the early voltage. Okay, so that's where we are with this configuration. Okay, that's where we ended up. So now today we're going to talk about a version of this amplifier topology, called the emitter degenerated common emitter amplifier, or generally emitter degeneration. Earlier, when we were working on the biasing part of the circuit, we also saw it. We saw that if we added this emitter resistance when we created the bias points, it gave us a more, I'll just draw the biasing circuit here that we would normally have. We would have something here, and we put something here. And by putting this, so this would be, depending on the VCC, you'd want to make the ratio of R1 and R2 such that the bias point of VN is around 800 millivolts, etc. To put this guy in maybe a little bit higher, because you would need to put some voltage across this guy. So we saw how that helped give us a more robust biasing technique. And it turns out that putting this emitter resistor not only allows us to have a more robust biasing technique, and by robust I mean we had less dependencies on the exact matching of R1 and R2. So that by putting this resistor here, it helped absorb some of those mismatches that you will normally get in a production environment. Not only does it do that, but it helps also stabilize your gain in the sense that it makes your gain more robust. It makes it more repeatable across various products with different values for the performance of the bipolar transistor. And we're going to see how that works. It's also done at a price, as we'll see. So when I first saw the emitter degeneration circuit, it didn't make any sense to me, because one of the immediate artifacts of putting a resistor here, this emitter degeneration action, is it reduces your gain. And I was like, well, isn't the whole point of an amplifier to get high gain? Why are we limiting our gain? And again, we'll see very soon here that we are giving up some of the gain for a more repeatable operation, more repeatable in production, which is when you're making real circuits on the job, that's all important. Okay, so anyway, so why does it? First thing first, I think the book does a nice job of talking about intuitively why the gain would drop. So imagine if, or you'd have less of a gain. Imagine if you had our normal common emitter amplifier, and you had a delta V in the input. Oops, let me clean this up. You had a delta voltage in the input. What that would do is all that delta voltage would go on the base, across the base emitter, and it would lead to a delta I sub C. So basically delta I sub C would be GM delta V. That whole voltage would change the current, because it's all being applied to base emitter. So an intuitive way to see why that won't be the case here, why that effect will be less, is you can actually see that this, if you put a delta V on the input here, it'll get shared between the base emitter and this resistor, because this voltage, this delta V, is going between this base and ground. So it's going between here and here. So some of it shows up between here and here, and some of it shows up between here and here. So not whatever shows up here is really not going to show up as a change in delta I sub C. So depending on the ratios of how much of it drops across the space emitter and how much drops across this resistor, you get less of a response with this delta V input. So you get, and this what it does is it improves the stability, improves the linearity, and also, as you'll see, it'll increase the input impedance of this device significantly. All at the expense of our maximum gain. So again, didn't make sense to me, when I was first looking at this class. In this class, of course, I went to a different school, different class, but when I was studying this topic. But trust me, this is like a very, very useful and very, very commonly used amplifier topology. Okay, so let's now define or derive the characteristics. Okay, so what the different variable, what the gain of this guy looks like. So let me just draw it here. So the small signal performance looks like a lot like a common emitter amp. So I draw we have our base and small signal R sub pi v sub pi plus minus. We have our GM v sub pi, the resistance R sub C, the load resistance, and our output is here. We have a resistor on the emitter, and we have our input here, Vn. And here we're assuming that R0, R0 would be out here. We're assuming R0 is 0. So we're not considering early voltage here. Okay, so the way to derive the gain of this is we notice that, if you look at this output node, you have a current G sub M going this way, and you have a current across the RC going this way. So the sum of these two has to equal to each other because there's no other current. So basically you have GM V sub pi is minus V out over R sub C. Or let me write it first, just to show you guys what why the sign looks like that. So basically GM V sub pi plus V out over R sub C is equal to 0. So GM V sub pi is minus V out over R sub C. Okay, so that's one dependency. And the other dependency, so that's one node when you're looking at the KCL of that node. The other node that we can look at the KCL of is this node here. So we have this current plus this current has to equal to that current. So if we call this current IRE, and I guess I'll call this IR sub pi, and this will just be GM V sub pi. Our currents would be IRE is IR sub pi plus GM V sub pi and R sub pi is V sub pi over R sub pi by definition. So let's just plug that in. So that's IRE. Okay, and the voltage VRE, so this would be this voltage here, is just defined as IRE times RE. So we basically multiply that by RE. Plus GM V sub pi times RE. Okay. So that's the voltage from here to here. And then this plus this is Vn. So Vn is going between the input and ground, where this point is. So basically Vn ends up, part of it gets dropped across V sub pi, and part of it across R sub E. So kind of along the lines of what we were saying here. So Vn, some of it drops across VBE, and some of it drops across R sub E. So that's what's happening. Whoops. That's what's happening here and here. Sorry about the background noise here, guys. So Vn is V sub pi plus VRE. So it's V sub pi plus this guy, V sub pi over R sub pi plus G sub M V sub pi R sub E. and this is equal to v sub pi 1 plus 1 over r sub pi plus g sub m re. Okay, so now to get a relationship between V in and V out, we can substitute this relationship for the relationship between V pi and V out in here. So, sorry guys, this seems like my bulldog just wants to make a lot of noise. She's just marching back and forth here. But anyway, sorry about that. Vn is minus V out over G sub M R sub C. Again, basically what I did was I said V sub pi is minus V out over G sub M R sub C. So I plugged this value in for V sub pi here. Got this guy times 1 plus 1 over r sub pi plus g sub m r sub e. Okay, so that's our gain, right? Or sorry, now if we do the ratio, then is the gain basically. So v out over v in is the gain. Okay, so that's minus GM, just remapping stuff here, moving stuff around in this equation, is minus GM RC, 1 plus 1 over R sub pi plus G sub M R sub E. Okay, so that's the equation for the gain, and we can simplify it. So let me just draw a circle around that, saying sort of that's the exact equation for the gain. Now, so remember the gain for the common emitter without the resistor degeneration was just this, minus GMRC. So now we're reducing this gain by this amount in the denominator, whatever that ends up being. Okay, so now we can simplify this a little by, if you just look at the relationship between R sub pi and G sub M. So basically by noticing that, or plugging in the value for R sub pi is beta over G sub M. So 1 over R sub pi is G sub M over R sub pi. So if beta is much bigger than 1, which it is, then 1 over R sub pi is going to be much smaller than G sub M, right? Because I can, oh, sorry, I put R sub pi here. What I meant was G beta. So 1 over, if beta is very large, then 1 over R sub pi is going to be much smaller than G sub M, okay? So we can basically end up zeroing this out compared to this 1 over G sub M value. So we end up with our approximate equation for gain. So put the wiggly cap there, minus G sub M R sub C over 1 plus G sub M RE. Okay, so this is simpler but approximate equation for gain. Approximate but good. Okay, so anyway, that's the equation for the gain of that device. Okay, so let's see what else do I want to say about that. Yeah, and I think we can just basically, the difference between this and this is we're just writing it differently. I mean, we're just moving G sub m around to get that. And the reason for that is a lot of times I'll do a quick example for us, but it turns out we can basically rule out 1 over G sub m compared to R sub e. So let's look at a typical example. So let's see, we got R sub c R sub e. Let's say this guy is 5k ohm. So this guy's 5k ohm. Let's say that R sub e is, sorry guys, the noise is starting again. So I'm gonna pause here and hope the noise goes away, and I'll try to patch on more of the recording. Okay guys, wish me luck here. So I try to find a quieter place now until the noise picks back up. Anyway, so where we were was I was gonna give you guys an example of, we derived this gain equation, and I said this is the approximate gain, good approximation. This is moving G sub m around, so this is just exactly this equation is exactly this equation with just everything, all the GM stuff moved into this one place. And the reason for that is because the idea is if you make GM sufficiently large, you can make this sufficiently small, and then your gain just ends up being RC over RE. And so as long as you make the gain large, your gain is exactly this ratio. Why is that good? Well, the good thing about that is then it doesn't matter exactly what your gain value is. So remember, G sub m is I sub c over Vt. Now, let's say I sub c changes by 25% for some reason. Let's say, your input base emitter value, your biasing, whatever, things are changing in production, and you get a 25% change in I sub c. Then you're going to get a 25% change in G sub m, and in a common emitter amplifier, if your gain is minus G sub m R sub c, if you get a 25% change in G sub m, you're going to get a 25% change in your gain from device to device. And that's not good. You really want to get very uniform gain. Okay, so let's use an example here. So let's say R sub e is 1k ohm, and so that's my circuit. Okay, and now let's say we assume initially, I'm not going to go through the bias point calculation, let's just assume that I sub c initially is 1 milliamp in the first device that we design. So the G sub m is I sub c over V sub t, and that is 0.0385 Siemens, or 1 over 25 ohms, or 26 ohms, sorry. Okay, so 1 over GM is 26 ohms. Okay, so plug this into our equation for gain for this degenerated case. You end up, basically the gain is RC over 1 over GM plus R sub E. So again, plugging it in, we get this is 5k ohm over 26 ohm plus 1k ohm. And this equals to minus 4.878. That's the gain of the circuit with a 1 milliamp current. Now let's say assume that I sub C changes by 25%. Again, you can get that because let's say your bias circuit here wasn't perfect. There's, you used cheaper resistors because, management told you this has got to get sold for a smaller amount, etc. So, this bias point moved up or down, and there's sort of this variation across your production again. So I sub C changes by 25%. Let's see what happens. So now, let's say that 1 over G sub M. So this is for, so I sub C now equals to 750 microamps. So 1 over G sub M is 34 ohms. So A sub V in this case ends up being minus 5K over 34 ohms plus 1K ohm. And that equals to minus 4.8325, excuse me. So now notice that the difference between these two gains is about a 1% difference. So you had, your bias was all over the place. You had 25% variation in your collector current, but only a 1% variation in your gain, which is like a huge win. That means, from in your product, from device to device, you're going to have a lot of leeway. Now you can use, basically it all translates to production cost. You'll have to do less testing. You can buy cheaper components, and the list goes on once you have this kind of indifference to variability, which is great. Now, but this came at the expense of lower gain. You guys remember, the gains we were sort of kicking around looking at in the common emitter case was, I don't know if you guys remember the numbers, we were talking about gain of 30, gain of whatever, those kind of numbers, 30, 34, 50, etc. So, the maximum gain of this, you can reduce, in this case, we can reduce R sub E to some extent and, increase our gain. So this isn't the bottom line. I just picked R sub E to be 1 kilo. But as we reduce R sub, let's say we used 100 ohms here, right? For R sub E because we wanted to get a gain of 48. That's what that would do. Now, in the denominator, we have something that has a gain of 100 getting added to 26 ohms or 34 ohms. And now you won't have as much, the difference between if you're adding 25 ohm to 100 or 34 ohms to 100, that difference in gain, although the gain may be higher, the delta is going to be more, right? Because the reason the gain difference here in this particular case wasn't very much is R sub E is you're adding that variability to a big number and it sort of washes out. It's a drop in the ocean there. But so as you reduce R sub E, you increase your gain, but your variability starts going up. And at the ridiculous extreme, R sub E is 0, and you just have the emitter connected to ground, and then you have all the variability shows up basically. All this 25% shows up in your gain, and you're exactly a common emitter stage. So there's a trade-off you got to make. But anyway, that's the emitter degeneration. And there's a couple of examples, which are pretty quick examples in the book. So here's one. And then again, this is working off the idea that, once, let's say you wanted to figure out what the gain of this stage looks like, okay? You could either go through and do all the calculations and come up with the small circuit model, blah, 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 Or you could recognize in this case that you have an emitter degenerated common emitter stage connected to the base of a bipolar amplifier. Okay, and as long as the bias points are correct here, let's say this bias point, this was assured that, given VCC, given this input, given a value for Vn, given this input, this guy was in forward active mode of operation. So immediately you would know that this guy's input, that this resistance going into this point is R sub pi, because that's the input resistance of a common emitter bipolar stage, is R sub pi for this device. Okay, so basically all you do is you have a situation where this looks like an emitter degenerated stage, but the gain is now on the denominator is RE in parallel with the input resistance of this transistor, and you can get to the gain much faster. And just this R sub pi 2, you just have to calculate it from the, the current, the GM of this guy and the beta. Another example is sort of a similar thing, and we'll see why this is the case when we're going to calculate the input-output impedance. But let's say I have a similar type of device now hanging on the output node, and then you realize exactly the same thing, as this is a emitter degenerated circuit, and this is a common emitter circuit here. So the input resistance here is just this R pi of 2. And so when you look at the gain, it looks like R sub C is in parallel with R sub pi 2. Remember, when you're looking at something like the gain, you're thinking about the small signal parameters. So whether this, this resistor is hooked up to VCC, this resistor is hooked up to ground, but in the small signal domain, both of these guys, so VCC is shorted to ground anyway, so it looks like it's RC parallel with R sub pi. Okay. All right, so let's look at the, one weird thing about the emitter degenerate case, and I would guess, like, I don't know, probably maybe 25% or like half of you are gonna fall into this trap in a test or in real life. Okay, so pay attention to this one, because now we're gonna look at the input resistance of a emitter degenerated common emitter stage. Remember, if you had a common emitter stage, so just a common emitter stage, and we looked at the input impedance, it was just R sub pi. Okay, now in this case we've added a resistor here. So when you look at the input resistance, it's tempting to say R in is equal to R sub pi plus R sub E. It's tempting to say that, but it is absolutely incorrect. Not correct. Don't do that. I still, to this day, sometimes I just jump to that conclusion, and it's absolutely positively wrong. Okay, so just remember that's not, whenever you see this, if you remember that, like, to sort of double check your input resistance, which will become important at work or on some tests. Just saying. So let's figure out. I'm gonna do a sort of drive the input resistance, which I'll go through it pretty quickly here, but we'll see that it's not. It is not this. So this is not the right input resistance. Okay, so let's do a quick calculation or a quick derivation of the input resistance. So input is R sub pi, V sub pi plus minus And then we had R sub E, there's a V of R of E across that. Then we have a G sub M, V sub pi, and that goes to R sub C and ground. We have V out. Okay, and then remember that when we're trying to do input impedance or resistance calculation, we put a test input, a perfect test input, V sub X, and then we measure the current coming out of it, and that ratio ends up being R sub N. Okay, so let's now derive what this I sub X and V sub X are going to be. So let's see. So again, we want to look at this node here. We've got a few different currents going into here. We have a I sub X is flowing through V sub P, through R sub P. So this is just the current flowing through here is just I sub X. Okay, so that's coming from this direction. G sub M, V sub pi is coming through this direction, and then the voltage across this resistor is pulling the current down. So let's look at all those things, okay? So I sub X is equal to V sub pi over R sub pi by definition. So by definition, V sub pi is I sub X, R sub pi. We just don't know what I sub X is yet, okay? And then the current going through this guy, so IRE is equal to I sub X, so it's equal to this guy coming in through here, plus this guy, so G sub M, V sub pi, but I can substitute this into here and get I sub X plus G sub M, I sub X, R sub pi. And so this equals to G sub M, I sub X plus G sub M, R sub pi. Now G sub M, R sub pi, so this guy looks like G sub M beta over G sub M. So this is equal to beta. So this is equal to IX 1 plus beta. Okay, then R sub N, what does that equal? So the total voltage that R sub N sees is this voltage, this R sub N. So you get a current I sub X, but it's basically, again, this voltage plus this voltage makes up the V sub X, okay? So the other way to look at it is, we want to get the current over across R sub V sub pi, I'm sorry. So you end up having so we basically want to add, we want to add this plus this ends up being V sub X, okay? So if I want to say V sub X is I sub X, that is equal to V sub X, V sub pi, V sub pi plus V at RE over I sub X. And we start substituting stuff. This is V sub pi, so that's I sub X R sub pi plus VRE is just this IRE times R sub E, so plus I sub X 1 plus beta times RE, and we're dividing all of that by I sub X. Okay, so then the I sub X's go away, and you end up, this whole thing ends up equaling to, so R in is R sub pi plus, I'll just move this one, usually it's written like this, beta plus 1, R sub E. Okay. So again, the temptation is to say R sub N is R sub pi plus RE, which again is incorrect, because in fact the input, remember that you want the input resistance or impedance to be large. So in fact, the input resistance is significantly larger than this. It's because you're multiplying, instead of just adding RE, you're multiplying beta plus 1, which is usually in the 100 or so value, by R sub E, and you're adding it to R sub pi. So it ends up that the input impedance or input resistance of a emitter degenerated amplifier is actually, really good. It's really high, and that's a good thing. Okay. I'm not going to derive the output impedance, but let's just say the output impedance doesn't change and is just R sub C for emitter degenerate cases. Let me just write that down. So for emitter degenerated. Okay. So R in, R out, and we have the gain, and or basically gain, depending on how you write it. Those are the values for the emitter degenerated case. Okay, let's see. Okay, so let me do a quick example before we finish up here on emitter degeneration. Say, okay, then we can finish. Okay, so let's say we have this example of a emitter. So this is from example 5.24 in the book. And let's say you have an emitter degenerated amplifier. And what it says is that assume I sub C is 1 milliamp. And then this gives you a voltage gain of 20 without the degeneration. That means if I disconnect this guy and connect the emitter directly to ground, I end up with a gain of 20. And then, but also the voltage gain is equal to 10 with degeneration. So as drawn here. So, and then it says assume beta is equal to 100, and what does it want to do? It wants us to calculate R sub C, R sub E, R in, and R out. Okay, so let's do it real quick. So without degeneration, we've got a really simple case. We have the gain is minus G sub M R sub C. G sub M is 1 milliamp over VT. So, and then this is equal to 20. That's what it says. So R sub C is equal to 20 times, I'm going to have to get rid of the negative just because, it was more like absolute value is equal to the gain. Is 20 to the gain of mine, or you can just see minus G sub MRC is minus 20, either way. Is 26 millivolts over 1 milliamp, and that's equal to 520 ohms. So that's this guy. Okay, and then we're told that with degeneration, the gain drops to 10. Okay, so basically our equation is 520. Remember the equation is RC, the gain is minus RC 1 over G sub M plus RE for emitter degenerate case. So we have 1 over 1 milliamp over 26 millivolts plus RE. So now we want to calculate RE, and then RE ends up being 26 ohms. So that's our RE. R in is just R sub pi. Maybe I should just, let me open up another page here. So R in is R sub pi plus beta plus 1 R sub e. R sub pi is beta over G sub m, okay, or 100 over 1 milliamp over 26 millivolts. And that is 2600 ohms. So that's 2600 ohms plus 101, so that's beta plus 1, times RE, which is 26 ohms. So this ends up being 5,226 ohms, or around 2 times R sub pi. So again, with these numbers, you see that our input resistance is actually ended up being really good. Instead of being 2,600 plus 26 ohms, it ends up actually being twice what you would get with a common emitter amplifier. So you get a significant increase in input resistance, and this is one of the really nice features of emitter degenerated amplifiers. Okay, and then lastly, R sub C is just R out is just R sub C. I guess I should have said that we can assume that VA is infinite and R0 is 0. R0 is 0. R0 is infinite, sorry. So we end up R out is just equal to R sub C is equal to 520 ohms. Yep. Okay, guys, so that's it. And we have, I think, one more lecture left for next Tuesday. And then we're going to do a review